Nick, thank you for being so kind to put together this incredible presentation. I was totally wowed when I saw it, but knowing you and working with you for all these years, I would have expected nothing less. So I met Nick a number of years ago when he and his team at ATK, his prior employer, hired me to help them commercialize their technology in the MEMS aerospace industry. Nick is a mechanical engineer, a bachelor's from Cornell, MS PhD from University of Illinois, Champaign-Urbana, and has been in the harsh environment area. And that's one of the reasons I wanted Nick to be here, to really show you how harsh an environment this technology needs to be able to survive. Because if you can survive Nick Tiliakos' environment, you can survive it anywhere. You know, if you can make it there, you can make it anywhere, as they say. New York, New York. So Nick is now a new guy with GE Aerospace, acquiring Innoveering recently, and is a VP of Science and Technology and Advanced Concepts there. And Nick is an expert in thermodynamics and was an adjunct professor at the Mechanical Engineering Department in from 2000 to 2007 in Columbia in New York. So Nick, with all that good stuff, one more thing, 40 technical papers, 5 U.S. patents, and an ardent U.S. Yankee fan. Go, Nick.
Wow. Okay, well, thanks so much, Roger, for that kind intro. And also I want to thank MEPTEC and Ira, Rosina, and Roger and others at MEPTEC for giving me this opportunity. I definitely am looking forward to it, and hopefully I'll live up to that introduction. So today I'm going to review just a snippet of our work in sensors as it applies to the extreme environment of hypersonics. And I'll get to, for those that are maybe wondering what the heck is hypersonics, I'll get to that in a few minutes, in a few slides. Packaging these sensors is extremely challenging, and I'll also discuss some of those challenges and some lessons learned. We're still learning. We're always learning. Every sensor that we worked on here has a goal to be integrated into a hypersonic system, whether it be a ground system or a flight system. And each of these, whether it's ground or flight, pose different challenges, even for the same sensor. So if I have a pressure sensor that I want to test on a ground test article to assess its performance and predict it and measure it before we go to flight, taking that sensor and then putting it on a flight vehicle has, even though it could be the same sensor, it has different challenges and maybe even different packaging. So that being said, just want to give a quick overview of a couple of the challenges in packaging, embedding sensors into materials. That's extremely important and something that we're continuously upgrading and learning. So one of the objectives that I'm hoping to help out here today is to present to the MEMS sensors electronics community a perspective that is in a niche application, a perspective in sensor packaging for aerospace applications, in particular hypersonic propulsion systems, which is our bread and butter here at Innoveering. Even though this is a niche application, it requires a coupled understanding of multiple disciplines, and I'll get into each of these in a minute. Just a little bit of quick background. Like Roger said, Innoveering was a small company. 10 years we were in existence as a small company. We're about 55 or so miles east of Manhattan, in the middle of Long Island. We were recently acquired by GE Aerospace, so our focus is still on hypersonics, but now we have the backing, if you will, of GE Aerospace. So our bread and butter has been for a long time propulsion, hypersonic propulsion, also rocket propulsion. There are different subsets of hypersonics. I won't necessarily go into all of them, but the main focus is developing these propulsion systems, high-speed flight, and to be able to use these other enabling experiences that we have and expertise in sensors and controls. You definitely need to monitor what you're flying and what you're testing. You need to be able to assess the performance and how well some of your models, the predictive models that we have for predicting the thermal response of these systems of the vehicle, but also its performance as a thrust making device, the propulsion system. These sensors allow us to acquire that data, and then we take that data and use it to anchor some of our models. And it's an iterative process. We also have test and evaluation capabilities where we design tunnels, aero-propulsion tunnels that present or emulate or recreate this hypersonic environment. And then, of course, S&T. So our focus is the development of hypersonic propulsion systems for the nation. Just a very quick overview of some of our sensors. Some of the transduction mechanisms vary from acoustics, optical to plasmas. As a transduction mechanism, we sort of run the field in different types of measurement, of measurements, whether it be temperature, friction, or shear stress. That's the drag, let's say, on the vehicle. Oxygen concentration, that's very important. In an oxidizing environment, you don't want your materials to oxidize. So it would be very good to know the oxidation level, pressures, heat flux we're working on, and I'll show you a little case study of that. And also using acoustics to determine non-intrusively to assess how these materials recede. Some of them do recede, some of the materials recede, they ablate on purpose. You want to be able to measure that so that you don't hit a critical limit, which is the thickness of the TPS or the thermal protection system. All of these sensors, and they're easily over a dozen that we've been developing, myself and my co-authors, Dr. Daniel Bruvallaro and Dr. George Papadopoulos, we've been developing over the past 10 to 15 years. All of these different sensors require different packaging. There's not a one-size-fits-all. Now, there are some common threads that kind of maybe tie these together, and we'll get to that in a little bit. Continuing with some of our sensors, I won't dive into these too much, but we've looked at embedding sensors and composites. Some of these sensors need to be really small, like a eraser head on a number 2 pencil, to fit into some of the locations that are very volume constrained, if you will. That's the other thing in aerospace, especially for a flight vehicle, you're just volume constrained and weight constrained. So you want to make everything light, as strong as possible, and be able to fit in some very tight confined spaces. Here's some acoustic sensor that we tested at NASA Ames many years ago. And the packaging for this is completely different from, let's say, something that would be embedded in a carbon-carbon material. Just some collage of photos of our ground test facilities that we've designed and built. These are subscale. The nation has much bigger aero propulsion facilities in various Air Force and DOD and NASA locations throughout the country. But because of where we're located, we can't really go too crazy on the size of these aero propulsion tunnels. The purpose of these tunnels is to simulate the environment, the hypersonic environment, and I'll get to that in a minute. We do have some additive manufacturing capability. In fact, now as part of GE Aerospace, that has increased quite a bit, so we're looking on leveraging that. And we do look at new materials. Again, now with GE Aerospace, we've opened up our aperture to CMCs, ceramic matrix composites. GE uses them extensively in their gas turbine engines, and we're looking at leveraging those for future packaging solutions. I mentioned also the need for flight testing. Ultimately, in what we're doing here is to get to flight. The ground testing is great and it's very important. It's also much less expensive than the flight test, but ultimately it's to get to flight. So like I said earlier, the packaging design for a sensor, even if it's the same sensor measuring the same pressure, let's say, for a ground test article, it could be drastically different for flight. So we do have quite a bit of flight experience. We actually have flown one of our high temperature sensors on a sounding rocket at Wallops Island. We're also looking at using an old F-104 fighter to test a supersonic regime, let's say Mach 1.5 to 2. And one of my sensors for high-speed indicator of Mach number will be flying in about 2 months on the Stratolaunch hypersonic vehicle. Here's the hypersonic vehicle shown hanging off of a very large aerospace vehicle. So just quickly, and by the way, if there are any questions, I don't mind, just, jump in. Anyone who has questions, I don't mind answering them now. But very quickly, hypersonics is a regime Mach 5 and above. So think Mach 5 is basically 1 mile a second, 1 mile per second. If there were an aircraft that people could reliably use, you could go from New York City to Athens in a little over an hour. So right now, though, the focus is on mainly unmanned aircraft or missiles and projectiles for the DoD. Now, what does it mean to have a hypersonic propulsion system? So there are no moving parts. The front of the aircraft captures air. And instead of like a rocket engine, instead of bringing the air or oxidizer with you, in a hypersonic air-breathing propulsion system, the air is scooped up at very high speeds. It's conditioned, if you will, through a train of shock waves. You can think of the shock waves as a virtual compressor. Okay, the pressure rises, and then you inject fuel in your combustor, and then you have a very sudden rise in pressure, and you take that chemical thermal energy and transform it into kinetic energy, which is your thrust. There are a lot of differences between this and gas turbine engines. For one, a gas turbine engine can start from the ground. Hypersonic needs an initial kick. So you need another way to boost it to a takeover speed of, let's say, Mach 2.5. And then you can do that with a gas turbine engine or a rocket engine. The other thing is the hypersonic propulsion system is intimately integrated with the airframe of the vehicle. So that poses other challenges. So for example, here's a hypersonic aircraft. The engine is situated here. Here's the environment, about 57,000 watts per centimeter squared, about 1,000 or more degrees Celsius, which is a little over 2,000 degrees Fahrenheit at the nose. That does decrease to about 800 or so degrees Celsius here at the engine inlet, and then about 500 or so degrees C, or about 1,000 degrees F on the control surfaces. Now, this is just external heat loads. We're not even talking about the heat loads inside of the combustor, where you have very few sensors right now. Why are these sensors important? Well, we need to interrogate the engine. We need to interrogate the skin. We need to assess whether, our design models are accurate. How do you design the thickness of the metal or the thickness of the composite to survive these environments? Now, the good thing is, for right now, these environments are only sustainable for, let's say, less than an hour. The duration is very much dependent on the mission, which is it's a DoD mission right now. Now, we are using inlet sensors, high-frequency pressure sensors here with an algorithm to detect where these shock waves are located in relation to a rise in combustion pressure. And this is important because if your pressure here increases too quickly, it literally chokes the flow and you get what's called an unstart. So the engine literally regurgitates the flow out the inlet and you have a stall. And as of course, no aerospace engineer wants to hear that word. It's not good. A little bit, I won't go through all this detail here, but I want to sort of, again, tell you about the environment, that it's very challenging. A lot of physics, a lot of multidisciplinary things, aerodynamics, material science, chemistry, thermochemistry. And so embedding sensors in this system, you need to understand the environment. It's an oxidizing environment. Depending on the trajectory, you'll see high loads. You also might see very high G loads. So that's a different sensor or a different way to package it under very high G loads. If that's a projectile that, let's say, comes out of a howitzer, for example, the Army is interested in that. So you have high stresses, very large temperature gradients. You can go from about, like I said earlier, 1,000 degrees C on the skin to an internal metal temperature just before you get into the payload bay. It drops down to, let's say, 150 degrees C. So how you manage those heat loads is extremely important, not just for the sensor survivability and its performance, but for the overall survivability of the vehicle. Just quickly, I want to show you that one of the metrics we use when we look at packaging is yield strength. We look at the yield stress divided by the density of the material. That gives us an idea of how much it weighs in relation to its strength over a very large temperature. So we're living in this regime right here. Depending on where you're on the vehicle, you might want to look at silicon carbide composites, CMCs, or metals. These are very expensive. So as you go further to the right, the cost increases tremendously. Now let's get to the packaging. Of course, I completely agree with what Roger said earlier about the packaging. It should be concurrent and early on in the design process. You can't segregate the two. You can't have the MEMS die designers separate from the packaging folks. They need to understand the environment. Everybody needs to be on the same page with regards to the environment. You need a methodical approach in terms of using analysis where it's necessary, design for manufacturing of the packaging, and also the MEMS chip. Now, this is an iterative process, which is this is sort of my thoughts on the steps. But these steps could be slightly different depending on your sensor type or where you're locating it in the system. But overall, it's an iterative process, which makes it very expensive. So the packaging design has many different challenges. So I'm going to spend a little time on the next two charts here going over these challenges. And I probably could have added even more challenges. But in terms of the MEMS die attach, that's extremely challenging for so many reasons. Selecting the adhesive, selecting the die attach material, applying it properly so that you don't get a chip, that's lopsided. We found that unfortunately, very high temperature adhesives, we don't know the properties. The vendors don't supply them to us, or they just don't have them. Also, we've noticed there are instances where the compatibility of the adhesive with the surrounding packaging materials or even the interconnects or the connections is an issue. Surface tension, a lot of these packaging in this cartoon that we show here is done manually. We don't, these are, we're not generating thousands of sensors a month or even a year. It's definitely not the case. We're lucky if we generate 20 sensors. And again, we test them. So from the die attach, the electrical connections, this is extremely challenging, we found, and you can imagine why. The backside electrical connections, making them reliable, making them integrable, being able to integrate them into the packaging is critical. And of course, taking the signal from the chip level to the data acquisition or an amplifier, whatever driver electronics is also challenging. Materials, that's why I spend a little time on materials. The parent material shown here and the sensor materials, it's extremely important to really track these materials, track their thermal properties as a function of temperature, to run 1D or even 2 or 3D analyses, thermal structural, to get an idea of CTE mismatch is a killer. In one of our sensors, the mismatch between the silicon and the metal packaging could be as high as 5-fold. So, you're not going to get everything to match. The question is, how do you manage the thermals? How do you manage the thermal loads, to dissipate them and carry the heat away so that you don't induce thermal stresses, which can, of course, really wreak havoc on the reliability of your backside connections. The other thing that I shown here in this little cartoon is because we're in hypersonic flow, if the chip protrudes into the flow or the packaging system protrudes into the flow on the order of even 0.5 millimeter or more, you're going to have shock waves here that are at the very least going to perturb your measurement. So, you have thermal challenges, thermal structural challenges, induced stresses, mismatches between your materials. Survivability, durability, reliability, it is just, I think that's kind of obvious. It's extremely important. Let me jump back here. There's an interesting problem too. If your parent material is an ablative on purpose, you ablate so that you absorb the heat and then you ablate. Aerospace engineers sometimes like to use ablative materials because it efficiently carries away the heat. So you ablate their material. If this material ablates and your packaging sits there, at some point it's going to be exposed. So in that scenario, you want your packaging to be the exact same material as the ablative. So in essence, your packaging is consumed. Now, again, these are short duration missions, anywhere from a couple of seconds to several tens of minutes. So integrating, that's what I said earlier. You don't want the packaging to protrude. You need to be very careful on selecting materials. Fabricating, curing time of adhesives. There are times when we had a really good adhesive, temperature-wise, it was very capable, but it was too viscous. It was very hard to apply it onto a 1 millimeter square chip. Packaging, inspecting the packaging, making sure you have good quality is also challenging. So metrology is a big deal. And then I've already mentioned some of this. Small form factor always poses a challenge for the materials. I won't spend too much time here, but we've done some work in integrating sensors and carbon-carbon composites. In this case, the packaging material was a carbon-carbon composite, so that there was no mismatch between what I call the parent material and the sensor packaging, and that mitigated some of the challenges I mentioned earlier. Continuing with the sensors, embedding them into other materials and packaging, you can see here from the CT scan, definitely some challenges in getting adhesive all the way there. And we also found through some modeling that if you don't know your adhesive properties, like Young's modulus of the adhesive and other thermal properties, you could get drastically different answers and predictions as to how the packaging will respond, thermal-structurally respond in the environment. Just a quick case study. We have a micro heat flux sensor here for the Air Force we're developing. It's 1 meter squared. We looked at the parent material, in this case, a metal, and a ceramic packaging, and then the MEMS chip. It's a typical silicon die. We embedded about 7 or so thermocouples so this is much larger than the sensor needs to be. And we wanted to get a feeling for how much what the magnitude of the temperature gradients was. We also have here predictive tools to predict the aerodynamics over the sensor. And that's always helpful because a model is very good to help you predict things. One of the things we learned from performing the thermal structure analysis, from performing a model, is that the ratio of the thermal properties and the density, so rho CPK of the parent material to the sensor, you'd like that ratio to be as close as possible to 1. So this is a little bit of a metric for us that we found is helpful, so that you avoid some of the CT mismatch as I mentioned earlier. Shown here is the results of that study where we put the sensor that I showed you earlier into the tunnel. And this sensor is a thermocouple that I think that was outside of the packaging. But you can see here, most of the temperature measurements were they matched very well, which was good. Very low gradients inside the packaging. And that was because the parent material and the sensor material were matched. So this data helped us anchor our models. And now we're going to extend that model to ceramics and see how far off the mismatch between parent and sensor packaging materials, how much that hurts us. So I'm almost done here. Last slide. Some of the lessons learned, and this is our heat flux sensor. This is a sensor that has a 1 millimeter square chip, MEMS chip. Some lessons learned. Again, consider the packaging and the material selection early on. Understand the environment that it's going into and being integrated. We came up with sort of a metric here, like I said earlier, to minimize the number and dissimilarity of the materials making up the packaging. Adhesive properties, we really need to understand them, and this is something that maybe we should invest time and money in here at GE, perhaps, to look at adhesives at higher temperatures. The biggest challenge that we find with the packaging is the electrical connections. We're going to look at through vias, like Roger mentioned earlier about through vias, and that's an extremely, something that we definitely want to pursue. So I think that's it. Again, I want to acknowledge the committee, MEPTEC, Ira and his team, and of course, Roger, and just the Air Force for funding the heat flux sensor program. Thanks again, and I'll take any questions.
HYPERSONIC.
Para calor.
Thank you in
You're
Greek.
welcome.
Questions. Ira, do you see any questions?
No, we have no questions from the audience, but I do have a question for Nick. I think in the environment you're working in, I mean, I'm assuming samples are hard to come by for all your testing. I mean, how
Yeah.
how difficult is it to do iterations? I mean, obviously you do a lot of simulations, but you need to, validate those simulations. So
Yeah.
how do you manage prototypes or, making samples and things?
That's a great question. That's why, well, what we try to do early on is, for example, this is a dummy. I don't know if you can still see the screen. That's why I didn't
Yes,
stop
we can.
sharing, but
Yeah.
okay. Yeah. So for example, here, this is made out of regular metal. I think it was stainless steel 304, which is relatively inexpensive. Yeah, it's not cheap. I mean, we definitely, we try to test as often as we can. The good thing about having the ability to have aero-propulsion, sort of subscale aero-propulsion facilities on site is we can take the sensor that we've assembled in the electronics lab and walk over to the aero-propulsion lab and test it. So we try to test components separately if we can, and then integrating them. We try to also piggyback on other programs to save money. So yeah, it's a good question. It's not cheap. And yeah, so like I said, we're not in production mode at all. We'd love to be one day, but right now we just want to get these sensors to perform and survive.
Now, Nick, I've got a question,
Sure.
and that is from being a MEMS guy and working with you in MEMS for quite some time. You showed a lot of MEMS technology. Can you talk a little bit about non-MEMS technology that you're using in these kinds of measurements?
Sure.
We saw optical, et cetera, et cetera. Can you talk about non-MEMS technologies?
Yeah, no, for sure, definitely. In fact, I would say out of the 12 or so sensors we're working on, maybe a third of them leverage MEMS technology. So we do use precision, micro precision type of machining. But for example, this sensor right here is a sensor to detect Mach number, and it does not use MEMS technology. We like to use sometimes we use what you call it laser etching and techniques to precision micro machining, but we don't always use MEMS chips. For example, here in this sensor, this sensor detects particulate spectroscopy. So, but behind this sensor, we have a small spectrometer, and what we use here is high temperature electrodes to generate a micro spark, basically a spark discharge. Very simple, actually. The sensor is pretty simple here. It's the back end in this particular sensor that gets complicated. The data acquisition, acquiring this data. For example, this particular sensor is a megahertz response. So here we'll use like some high temperature electrodes. Let's see. In this sensor, of course, we use acoustics. We use piezoelectric materials, piezo resistors. This is not in the flow. This is outside of the flow. There are times when we have to cool this. So yeah, we use a range of precision machining. We try to use materials that are off the shelf, nothing too fancy. I don't know if I answered your question, Roger.
Yeah, that's fine. Another question.
Roger, there are a bunch of questions that came in.
Thank you, Ira. Another question, very important to tie in what other things are coming in, is that we talk about the sensor, but what about the electronics? The stuff that other people have been talking about for the past 2 days. How do those electronics survive the environments that you're trying to measure?
Yeah, it's a great question. I'll keep it brief so we can let the other questions as well be answered. But for example, here's the electronics. So these are off-the-shelf components that we've assembled here for a flight vehicle. These are flight-rated electronics. We had to go through tremendous hoops, shock and vibe, and thermal testing. We had to test these down to minus 40 degrees Celsius. So we have a special automated refrigerator oven. We have three electrical engineers on site. So the electronics is extremely important. We try to use passive active cooling as needed. The electronics are also, not near the sensor. They're quite a bit away.
Yeah. Okay, great. Thanks. So we have, how much more time do we have here, Ira? We have
About
several-
4 minutes, 5 minutes. Yeah.
Okay. The next question here is, what are your metrology challenges?
Great question. Quite a few. I mean, so we do have, I mean, we're not a MEMS fab house, so, but we do have a 2D scanner from Chaos that we can measure, you know, the profiles of the chips or the sensing elements. We do have, you know, typical gauges that we can measure, you know, basic things. But for example, on the packaging, if we make them with an outside vendor, we have to rely on their first article inspection kind of thing. You know, the MEMS chip, we work with universities and use their clean rooms. So we'll use profilometers and things like that. Whatever metrology they have, we'll use them. I don't know if I'm answering fully, but I think that's what I recall right now. Yeah, we don't have tremendous metrology here. As we get more integrated with GE Aerospace, we hope to learn about, they have some very good metrology in upstate New York at their research center. So right now, that's all I can recall.
Thank you for that. This will be the final question, and the question is, do you have much success with commercial off-the-shelf MEMS and sensors, or are most of your technologies requiring custom devices in hypersonic environments?
Yeah, that's a great question. I would say in terms of our MEMS-based sensors, they are custom made, and we work with some of them. We make ourselves with when we have one of our engineers is well versed in MEMS fab. We go to a university in a clean room, so we don't mind buying off the shelf MEMS sensors and then packaging them appropriately. In some instances, we've done that with an accelerometer, for example. But because of the sort of the transduction mechanism we're using and the measurements, all of our sensors are multi-property. They don't just measure one thing, and we've done that by design. They'll measure multiple properties. So sometimes that kind of implies that we need a custom solution for now.
Do we have any more time for any more questions, Ira?
One quick one.
Another question is, with ceramic and sensor packaging and large CTE mismatch, is board level reliability a concern? If yes, how do you deal with it?
I mean, so yeah, the electronics, I don't know if I have a good schematic here, but the electronics, we have to keep, you know, so shown here, for example, the backside connections, you know, this sensor, let me just jump to the last slide. This sensor, for example, would be embedded so that its element is exposed to the hypersonic flow. And then this electronic, you know, these wires here would have to be in the payload bay where the temperatures are much lower. And so I think I'm assuming by back end electronics, you mean the acquisition boards and the amplifiers and things like that. That all has to be in the payload bay, and the payload bay has to be below, I think, 150 degrees or so.
Thermal basically mechanical thermal isolation.
Exactly. Yeah.
Yeah. Okay, I think that might be it.
I want to also thank Adventest, who's received the highest customer satisfaction surveys, ranking as the #1 large supplier of semiconductor equipment in 2022 from Tech Insights. Also would like to thank Omcor and Cadence. Collectively, their sponsorship has enabled us to produce this event and make it available to everybody free. So I want to thank them once again. And when you have an opportunity, please thank them. And lastly, I would like to thank everyone here for participating. We will have the slides up next week. YouTube videos, the first 2 days are up. The remaining ones will be up by next week. So I want to thank everybody and wish you a good rest of your day and look forward to seeing you at a future MEPTech event. Thank you.